Okay, so I'm Andy Strominger. This is black holes from A to Z. There's two TAs for the course, Mina and Monica. And their information is all on here. Black holes have become a huge subject with many different aspects, from astronomy to mathematics to physics to philosophy and history of science. And I'm not going to cover everything in this course. I'm mainly going to cover the things I like the most. And however, we'll correct to that to some extent, and that we're going to have 5 or 6 guest lectures during the course. And these, except for Maldacena, does everybody have a syllabus? Okay, I guess we should have printed them, shouldn't we have? I guess it's on the website, but maybe you could run it. Yeah, thanks. And so this is also, Harvard as of this year has a graduate program interdisciplinary program in black holes. So if you're a graduate student, you can get a degree in black holes. And there's something called it's associated with something called the Black Hole Initiative, which studies black holes from an interdisciplinary point of view. And this course is one of the approved courses of that program. And the other faculty members leading the initiative are all going to give guest lectures. That includes, I guess you don't all have the syllabus, but Professor Yao from the math department, who will talk about mathematical aspects of black holes on February 20th, February 27th. Juan Maldacena, who once was a professor here, now at Princeton, is going to give a guest lecture probably on quantum aspects of black holes. Avi Loeb, who's the director of the Black Hole Initiative, will be giving a lecture and on astronomical aspects of black holes. He's worked on a lot of different things. I'm not sure which one he'll be talking about. Shep Dolman, who's building this very exciting Event Horizon telescope, and maybe even the data will be out in time, will be announced in time for his lecture on March, maybe that's wishful thinking, I don't know, on March 13th. And Peter Gallison, he might change his date, but he does very interesting work and is making a movie on the history of black holes and the philosophy of black holes. And you're all welcome to, I'm up on the 4th floor here, and anybody is welcome to knock on my door at any time. And it's a 2-hour class, but we'll take a 5-minute stretch break in the middle. I like questions, so please pipe up and ask questions if I'm saying something that, or you want to know something, or I'm saying something that's not clear. Probably, if you have a question, there's at least one other person in the audience who does. As far as reading, probably the closest thing, so I'll talk mostly about quantum. Well, the first half, I guess, will be just I really am going to start from the beginning with the properties of the Schwarzschild solution and Penrose diagrams, causal structures, and all that. That will take a little while, but I do want to get to some quantum aspects of black holes. Also, it looks like, it's not certain, but it looks like I'm going to teach us, make this into a 2-semester course, and with the second semester being next spring, and which still isn't really enough time to cover all the interesting aspects of black holes. I think my main goal in this semester is to get to a clear statement of the information paradox, and which takes, you have to lay a lot of groundwork before you can even sort of say what it is in a sharp way. So I guess that's all the administrative things I can think of. Does it cheer for you right there, Scott? Any sort of questions about general administrative? Oh yeah, there's also, I just discovered yesterday, there's a bootleg copy of notes from the last time I taught the course, which is on the web. I'm sure you'd all find it sooner or later. Read at your own risk. I haven't read them. I haven't checked any of the equations. I don't know what I can't be responsible for anything I said 4 years ago. It might have been it might have been transcribed. I don't know. In fact, I found one mistake in there just when I look at it. So, so that's that. Any kind of questions, administrative stuff? All right. Oh, and yeah, it's helpful. I'm sure there's some number of auditors in here. It's helpful if you enroll. It pays the TA salaries. And also, there's going to be, oh yeah, a homework. Yeah, that's all presented in the course description. It's a homework. And, you know, if you do like half the homeworks, that would be, if you want to enroll pass-fail, you know, come to all the classes and do half the homeworks or something like that. Okay, so yeah, I guess if you want to enroll pass-fail, I probably need to sign something, so we could talk about it then. Okay, so as I said a moment ago, in the last decade, black holes have moved into center stage separately in different areas of okay, Monica's got the syllabus there. Separately in different areas. First of all, when I was a graduate student, lots of people didn't even believe they existed. And it's hard to say when people started believing in black holes, but I think it's fair to say that you know, an astronomer who didn't believe that black holes existed would now be considered a crackpot. But that's only in the last 5 years, well, especially since LIGO. And of course, what has happened, you know, pretty good evidence, you know, Ramesh Narayan gave some of the first evidence from looking at the X-ray spectrum emitted from dark regions in the sky and matching it to what you would expect from a black hole. That was decades ago that happened. And of course there was the binary pulsar. But now we don't really have to guess very much. We think that for some number of years now, we think that there's a supermassive black hole in the center of the galaxy. There's, a big dark spot there that things are orbiting around. And then, of course, we had the spectacular discovery of, there's a seat right there, and there's a seat right there. And there's one right there. And there's 3 of you. There's at least 4 seats left. Yeah. So there's a huge black hole in the middle of our galaxy, and we're orbiting around it, and you can look at the orbits of the stars. They all point to the same region, and you can make a very precise estimate of the mass and so on. And of course, you can't see the black hole because light doesn't come out of the black hole. But in fact, the main evidence for that is looking at the orbits of stars, but it does have some sort of mysterious glowing gases around it that emit in a pattern consistent with, the kind of magnetospheres that you expect around surrounding a black hole. Then, of course, there's LIGO, which just was a spectacular match between the numerical simulation of the gravitational wave form for 2 colliding black holes, not neutron stars or something else. That was a very visceral image of black holes. And then what is going to be sort of even better of course, LIGO also told us something about gravitational waves, not just black holes. But I'm very excited about is this beautiful Event Horizon telescope, which Shep will give us a lecture on, where, as the years have gone by, just like we get more and more pixels on our TV screen, they've got more and more pixels in the sky. And the size of the biggest black holes in the universe, sort of the solid angle in the sky, both the one Sagittarius A star in the middle of our own galaxy is about the size of an orange on the moon. And then there's also M87, which is like 1,000 times bigger and 1,000 times, the one in the center of galaxy M87, 1,000 times bigger and 1,000 times further away. So it's the same size up in the sky. And by stringing together all the telescopes on Earth, they're hoping, in fact, they already have collected the data, but it isn't released yet. But they hope to get something like 10 or 20 pixels in the region occupied by these 2 black holes, which is orders of magnitude more resolution than anybody has achieved before. So so there's all data, astronomical data on black holes is just starting to pour in, and as it becomes a real experimental observational subject, we start to understand, as we try to predict the results of the experiments and so on, we start to understand that we start to realize we didn't understand black holes as well as we thought we did. That always happens when you try to make a detailed prediction. Whoops, how do I deal with this equation and so on. So it's been, it's not just the astronomers sitting there collecting the data, the theorists trying to understand the black holes are faced with some challenges. And indeed, in the case of LIGO, getting that signal out, getting the waveform out, if they discovered it 10 years earlier, they'd have known they'd seen gravitational waves only 10 years earlier, right? They'd have known they'd seen gravitational waves, but they would have no idea what the source is, because it's such an incredibly complex problem, which required major breakthroughs in understanding how to write computer algorithms for general relativity simulations. But that was done just in time for LIGO to see the black hole. So it's exciting for everybody. Black holes are also, and general relativity in general, is also a source of great inspiration to mathematicians. And if you write down a differential equation with random variables and so on, random coefficients among the different terms in your equation, it's very likely that solutions won't exist, or they'll become singular after some finite time evolution and so on. And if you write down the equations of general relativity, they're differential equations, they're highly nonlinear, and if you just written them out and showed them to a mathematician, any reasonable mathematician would have taken 1,000,000 to 1 odds that there was no good behavior of those equations, if you didn't know where they came from. So there are all sorts of interesting mathematical properties of the equations of general relativity, which are still incompletely understood and really comprise a whole field of mathematics, and moreover have inspired existence of solutions and have inspired developments in other fields. And we'll hear a little bit about that from Professor Yao. Also, the history of black holes is kind of fantastic. Einstein wrote down his field equations. It said nobody will ever solve them exactly. Schwarzschild solved them a couple of months later, and then died, not knowing what he did. Then people argued for 50 years about what the solutions meant. I don't think it was until the 60s that the theorists agreed on how we were supposed to think about these solutions because of the various coordinate singularities and so on, and how they behaved, even sort of the basic things. And it's very surprising that you would have an exact solution in hand, and that it would take 50 years to understand what it meant. And then, of course, shortly after that, Hawking came along with throwing the quantum aspect in, and we still haven't unraveled that. And it's also interesting to philosophers what it means to have a region of space-time about which you can have no knowledge, even in principle. So, but those are not things that I'm going to talk about. So what I'm going to talk about is, what to me is the most interesting equation in modern physics, which is the Hawking Beckenstein area entropy law. Wait, I think the C cube goes down here. And so this is a very puzzling equation. So it relates, on the left-hand side, we have the entropy, which is a concept in thermodynamics, stat mech, information theory. And on the right-hand side, we have geometry, general relativity, I guess. This is the area of the event horizon of the black hole. And we have quantum mechanics. And special relativity, speed of light. And then there's a number here. So it's a math equation. And it's important that it's a math. I mean, it's this 4 is really important. It's not. There's not a squiggly line there. It's a number. And the fact that it's a number is such a precise universal number is surprising, and is hard to understand. The C cube goes on top. Sorry, I usually set it to 1. Okay, so and this formula was just inscribed on Hawking's headstone in a slightly different form in Westminster Abbey. Now, so this formula ties together kind of, it's not a formula in some field. Relativity has its formula. The general relativity has its formula, the Einstein equation. Quantum mechanics has its formula. The Schrodinger equation. Statistical mechanics has its formula, which is, the entropy is a function of the number of states. So fields of physics have their own formula. This is a formula which involves all fields, ties together all the different areas of physics. So we know that there must be something very important about it. And it's a universal formula. It it applies not just to black hole horizons, but to any boundary of a region of space-time that is causally inaccessible, like a cosmological, in particular, a cosmological horizon. And indeed, the properties predicted by this equation of cosmological horizons, one could argue, have been measured in seeing the fluctuations in the context of inflation and seeing the fluctuations in the cosmic microwave background. That's a controversial statement, but some people would say so. And but the very best thing about this formula is that we don't understand it in any really deep way. We know it's true because we've tested it in a lot of different contexts, but we don't know why it's always true. Sort of consistency forces it to be true, but what is the deeper origin of this equation is in my mind, one of the great unsolved problems of modern physics. And we also believe, or many people believe, that when we do so, it's been so hard to understand why a relationship like this would hold, that that when we finally do unravel this, that it will lead to a very fundamental new view of the nature of all the things in this equation, namely space-time, quantum mechanics, and information. And probably a new view of the universe comparable in its impact to the views brought about by quantum mechanics or general relativity. And that's why it's an exciting thing to think about. Now, one of the, there was a very simple argument that was given by Hawking in early 70s that that this represents essentially the information content that can be stored by a black hole. And then Hawking argued that black holes evaporate, and when they disappear, all the information is lost. And now, there are lots to say, and we'll say it and we'll discuss it. And there are objections to this argument and so on, but there are some things that we feel we understand very, very firmly. Almost nobody thinks the argument is right. There are only 2 people in the world that I know of that confess to thinking the argument is right. And there are maybe 10 people in the world who think they understand why the argument is wrong. I'm not one of them. And of those 10 people, I don't think there's anybody else who believes that they have correctly understood why the argument is wrong. So none of those people have convinced anyone but themselves that they figured it out. So it's a huge puzzle, which has stumped all kinds of people, but nevertheless one that we have a lot to say about. And when I think back on it, it is amazing how much we've learned trying to solve this puzzle without actually yet solving it. We've learned all kinds of interesting things about the nature of space and time and quantum mechanics and the holographic principle and many other beautiful things, but we haven't yet solved the problem. Now, why are people so reluctant to accept Hawking's argument? Well, if information is lost, then the foundation, the basic assertion, the minute you start to do physics, is that there are laws of physics. And moreover, that those laws of physics determine everything, in the sense that if you have perfect knowledge of the present, and perfect knowledge of the laws of physics, that allows you to completely predict the future and to retrodict the past. It's very hard to imagine, and I've never heard a concrete suggestion of what it would mean for laws of physics for the universe. Now, we're not saying that we know all the laws. We're just asserting that they exist. And I think Newton essentially asserted this, if not even before, but it's very hard to imagine what it would mean. The laws of physics are true most of the time, but every once in a while something happens that doesn't obey the law. What would that mean? Okay, we don't know how to think about that. Where did that thing come from, and how do we describe what the things we just can't describe, or So if you accept Hawking's argument, which we will go through in more detail later, that information gets swallowed by a black hole and a black hole evaporates and the information is lost forever, then you're giving up on the idea that there are laws of physics, and you're giving up on the notion of determinism, that, as I stated a moment ago, that the present plus the laws of physics determines perfectly, in principle, both the future and the past. And we just don't know what to do without it. One way this could have gone was some clever person figures out some way of describing the universe that is a little bit less than having laws that determine everything. But there's no proposal for that. And partially the absence of such a proposal and the various things coming out of string theory and other kinds of ways of thinking about black holes have made the idea that determinism remains exactly valid in the universe, even in the presence of quantum mechanical black holes, more and more plausible. Certainly, Hawking himself recanted his original assertion a decade or two ago. So I find that this all very exciting and a lot of fun. And so what I'm going to do in this course is, start from, a discussion of causal structure and Penrose diagrams and talk about the black hole solution. Yes.
So can I ask a very main question?
Yes.
So we're upset about the loss of determinism in physics. What about
Good question. Quantum mechanics is deterministic in the sense that if you know the quantum state at any moment of time, you know the quantum state at any later moment of time. That's the statement of exactly. What happens in quantum mechanics is that position and momenta are not simultaneously observable. They don't commute. But there still is a notion of unitary evolution. If you know the quantum state at one time, we don't usually use the word determinism. In quantum mechanics, we use unitarity.
Yeah, but some people take measurement very literally, in the sense that if you make a measurement, you're changing the state and most of the time. Like we would not normally take that point of view, but there are some people who still.
Well, if you make a measurement and you throw out the correlation of the measuring device then throwing out that piece of information destroys the unitarity by hand. So, but if you keep track of everything, the entire universe should evolve in a unitary manner. So this kind of uncertainty is much worse than, and very different, more severe than this kind of uncertainty is worse than the uncertainty in quantum mechanics. Okay, so I want to talk about causal structure. So the simplest question that we can ask about two space-time points, x and x prime, is what their causal relation is. That is, can some action at x affect a measurement at x prime and vice versa. And in answering that question, what we want to know is if we look at a path p from x to x prime, can we find a path that is, if p is everywhere a space-like trajectory, then we say that x and x prime are space-like separated. If p is everywhere time-like, then we say that they're time-like separated. And if p is if neither is possible and there's a null, a light ray that connects x and x prime, then we say that they are null separated. So if we're given a point x and we draw the future light cone of x, then there are three different, well, actually, there are 5 different possibilities. We can have x prime up here could be in the future light cone. So this would be the future light cone, or the interior of the future light cone. This is the past light cone, or the interior of the past light cone. So x prime can lie in here, it can lie in here, it can lie in the space-like separated region, or it can be right on the boundaries on the light cones. So there are 5 different kinds of causal relationships that x prime can bear to x. Now, this is just in some local region, but if we have a bigger space-time, or a black hole space-time in particular, or a cosmological space-time in general relativity, all kinds of strange and crazy things can and do happen. And we're seeing them happen now with telescopes. So the causal relation in our universe of different points does not follow the simple intuition that I've just, is not captured by the simple intuition that I've drawn on the board here, and requires much more careful and detailed thinking about that. And so if we have a space-time, we want to be able to draw a diagram of it. And there's some very nice kind of diagram. Actually, I should use this one first. Yeah.
Just according to that definition, like every 2 points time stay like separated, even if they're time like separated. Like in Mikos space-time, if you take a point really far away from x, and then if y is in the future light cone of x, then path going from x to z, that point really far away, and then from z to y would be everywhere space-time separated. I think, yeah.
Well, we have to turn it there.
To, like, call 2 points space-like separated if they're not
Sorry?
I think it would be better to call 2 points space-like separated if they are not time-like separated, or there is like there's no time like that. Yeah.
You're absolutely right. You're absolutely right. Yeah. You're absolutely right. Thanks. Okay. So, so what we want to do is to draw a Penrose diagram. And what is a Penrose diagram? Well, one condition for a Penrose diagram is when we draw a picture of the space-time, we demand that light rays go at 45 degrees. Okay, so we use units in which light rays go at 45 degrees. And let's start with Minkowski space. I mean, we're going to do more than this before we get to the Penrose diagram. But let's start with Minkowski space. And I can draw a picture like this. So the line element for Minkowski space, the metric we can write is minus dt squared, where t is time, plus dr squared, where r is the radius, and then plus r squared d omega 2 squared, where d omega 2 squared is the round element, the round metric on the unit 2-sphere. And so we could draw a picture of Minkowski space in which the vertical axis is t, the radial axis is r, and we draw it, and then each point here is a 2-sphere, except, so each point would be a 2-sphere, except for the origin, which is just a point. So you have a series of nested 2 spheres with a point in the middle that fills out a 3-dimensional plane. And then we want to choose our units so that a light ray going out from the origin looks exactly like this. And then we can see that at fixed angle, that if we have any 2 points, like here and here, if they're inside this 45-degree thing, then this one is to the future of that one. And if they're inside here, then this would be to the past. And here they're space-like separated, and so on. So the 45-degree light rays are always, units are always used so that light rays travel at 45 degrees on the blackboard. Now, there's something bothersome about this diagram. And what's bothersome about this diagram is that we're not drawing the entire space-time, right? We can't fit the entire space-time on the board. It goes off to infinity. And we're going to be very interested in the structure of infinity. We want to talk about it. We want to label points on it. And we don't want to always have to be waving off and thinking about something infinitely far away. So what we would do would be, what we can do is the following. Let's define u equals t, new coordinates, u equals t plus r, and v equals t minus r. So lines of constant, this would be a line, it's t, this would be v equals constant. So lines of constant v look like this, and lines of constant u go the other way. And then we have that ds squared is equal to minus du dv. And by the way, I like to choose my null coordinates so they always get bigger as you go to the future. I mean, I could have written r minus t, but this is how I usually do it. Minus du dv plus r squared, which we should regard as a function of u and v. It's a half u minus v. d omega 2 squared. Okay, so, well, that hasn't helped us too much with this infinity problem. But now we want to write u is equal to the tangent of u tilde, so that when minus infinity when u ranges from minus infinity to infinity, u tilde goes from minus pi over 2 to pi over 2. And then we have that ds squared is equal to minus du tilde dv tilde. I'm just doing the coordinate transformation. Du tilde dv tilde plus r squared, which we now think of as a function of u tilde and v tilde, plus d squared omega 2. Now, it's not very hard to take these derivatives. You've probably already done it in your head, but we don't actually care about the form of this function here, except for one important thing. It's everywhere except at the boundary. It's everywhere positive. In other words, there's a one-to-one. There's a good coordinate transformation. There's a one-to-one transformation between u and u tilde. Now we write this as equal to du tilde dv tilde of, so this is one of these things that it's all looking very simple, but suddenly we're going to come across something that is a little surprising and non-trivial. Minus du tilde dv tilde plus r tilde squared. So we have to redefine it by this factor. But it's still some positive number, which is all we care about, d squared omega 2. Now, and I'm going to call this ds tilde squared. Okay, so now the important point is that if the causal structure of the geometry described by ds tilde squared on the plane is the same as the causal structure described by ds squared, because they differ only by what's called a Weil factor, or a Weil rescaling. That is, the metric is the same up to multiplication by an everywhere positive constant. And position-dependent positive constant. But it's positive everywhere. That's the important point. And therefore, since it's positive everywhere, the answer to the question of is the tangent vector along some line connecting 2 points positive, 0, or negative, the answer to that question will be the same in the tilde metric, what we sometimes call the conformally transformed metric, as in the original metric. That is, the causal structure of the new space-time geometry, ds tilde squared, is identical to the causal structure of the original Minkowski space that we were studying. Okay, but now this is nicer because so now we want to draw this picture. And what we've succeeded in doing here is pulling infinity into a finite distance. So let's draw this picture now in the tilde coordinates. And the first thing is, where is the origin? Well, the origin is r equals 0, which is u equals v. But if u is equal to v, u tilde, oh, I should have written here, v is equal to tangent of v tilde. V tilde is equal to v. And so we have that the origin is at u tilde equals v tilde. So I guess we have the v tilde going this way and u tilde going this way. Now, where is u equals infinity? What is u equals infinity? U equals infinity. Remember, lines of constant u look like this, and they were going off like that. U equals infinity is the place where light rays go to. And v equals minus infinity, at fixed u, is the place where light rays come from. And similarly, but u equals infinity is u tilde equals pi over 2. So u tilde is going this way, so we have a line which is u tilde equals pi over 2, which is the place where light rays go to. And then we have the place where light rays come from, which is v equals minus infinity, or v tilde equals minus pi over 2. And so this then, we've now succeeded in drawing all of Minkowski's space on a blackboard in a way that represents the causal structure. And let me remind you that every point on this picture represents a two-sphere, except for the origin, which is just a point. So if I take a line of these two spheres, it's an R3, and this point out here is itself a two-sphere. Okay, now these regions, they're very, let me tell you some names. This region, the place where light rays go to, is called future null infinity, or Scri plus. The place where light rays come from is called past null infinity, or Scri minus. Then there's the place where they meet, which is spatial infinity. If you go in a space-like direction forever, you get to spatial infinity. And then there's the place we'll get to if we live forever. That's called future time-like infinity, I plus. And then this is past time-like infinity, I minus. Okay, so just from this simple exercise, now if we take, say, an observer at the origin, then this region would represent the causal future of the observer, and this region would represent the causal past. And so one non-trivial statement about Minkowski space, one of the most basic ones, is that if you wait long enough, you can see everything. That is, when you get all the way up to here, the entire space-time is in your causal past. And it's basically the only space-time we'll encounter with that property. And well, maybe there's some refinements here. You might say that about anti-de Sitter space too. But it's not true, certainly not true in our own, we don't believe it's true in our own universe. It's not true in any space-time with a black hole in it. So it's not a generic thing. It's a very special feature of Minkowski space. Now, the other thing is that space-like infinity, that is, if you go that away instantaneously forever, is a much smaller place than the place where light rays go to. So if something goes to infinity, the only thing you can say about it is which point on this sphere it ends up at. So the ways of going to infinity are asymptotically only characterized by an angle on a sphere. Yeah.
Is there a problem with the, it's weird that the light-like infinity is a line rather than a point for the spatial, and will that always be true regardless of how we did this conformal transformation, or is there like a subtlety with the fact that the...
So I was just about to say something about that. So null infinity, on the other hand, is much bigger than spatial infinity. So the ways of going to null infinity there's many more. You can make the statement that it's a meaningful statement that one light ray, certainly if they're going at the same angle, one light ray got to null infinity before another light ray. There's an ordering there. And so it's a much richer place. And in fact, this richness in general relativity, there's a whole infinite dimensional group that acts on this and plays a central role in general relativity. It's called the BMS group. And so the fact that null infinity is much bigger in Minkowski space than space-like infinity is a very, well, it didn't take very long to derive it, but it's a very weird thing which has all kinds of all kinds of strange consequences. Now, generically, null infinity is it's a typical situation that null infinity is big. I don't know. That may just be that we like to study spacetimes that are something like our own. Yes?
Maybe just a follow-up question. So the description you just gave is based on this particular choice of Courant transformation to put it in a finite region and then pick a boundary. Can you just say to what degree it's independent of those choices?
Okay.
Different coordinate transformation also put it in a finite region.
Yeah. So so it would be unchanged. The conformal structure would be unchanged if we were to take this metric and multiply it by any function which is everywhere positive and non-vanishing. And that is what, so it has nothing to do with, the statements we made were coordinate independent. But the important thing was that these were actually, these are different metrics. Distances measured in these two metrics are different, and but their conformal structure is the same. So any metric we chose would lead to the same conclusion as long as it differed only by what's called a Weil transformation. Yeah.
You're doing a little bit more than that, though, right? Because you're also including the points of the boundary. So you're taking some computation, it's not as obvious to me that that's independent of the choice of file factor.
Well, I haven't been very precise about exactly what I was including and what the structure was out here. So, and in fact, that has been, there's a lot of subtle substructure down here, and that is a very delicate point, which I've lectured on elsewhere, but we're not going to try to get into in this course. But I haven't really asserted anything about the details of what's going on in this boundary. That's right. There have been different discussions of exactly what happens at the. There's been a long history of discussions of exactly what happens at the boundary there. Yeah.
You wouldn't get rid of null infinity though in any of those cases.
I don't know of any proposal where you don't have null infinity, but what kind of exactly what kind of structure you have out there is there's a very rich literature on.
Can we say that, like, if you have two different Penrose diagrams for one two-dimensional subspace, then the continuous map, like mapping one to the other one, also maps the boundary to the boundary, and since it's a conformal transformation, so it keeps the angles fixed, so the boundary is
Which is that you can imagine boundary too.
yeah, there's also like since we're doing this compactification, then we can like extend this so that like the boundary of this maybe it's not that.
I don't. You certainly can't just say it. Penrose started the subject of how you deal with this, and I would say basically Penrose got it very, very wrong. And there was a 10 or 20, 30 years of literature on this and the structure of how exactly you back divide the boundary. And then, Christodoulou showed that his, and other people were also aware that he really had made a very unphysical choice of how to maybe mathematically natural, but highly unphysical. And some people are still following Penrose, so it's a big and very interesting subject, but not the subject of this course. Yeah. Okay. Anyway, I found it surprising first time I saw this. The simple manipulation leads you to these. Okay, yeah, Minkowski's, but null infinity is a big place, and there's a lot of structure out there, and of course, in scattering theory, where you look from maps from past null infinity to future null infinity, this structure, is very important and might even completely determine some scattering amplitudes, just the consistency of this structure. So, I promised a 5-minute stretch break, so let's take our 5-minute stretch break. Okay, let's start again. So now I'm going to draw a couple of more Penrose diagrams for more. Okay, sit down, guys, ladies. Whoa. Okay, so what I'm going to do now is I'm going to talk about a couple of more simple examples. The simplest examples, really, de Sitter space, anti-de Sitter space, and then we'll go to Schwarzschild black hole. I don't know if we'll get there. We might get started today. Okay, so de Sitter space is a solution of the Einstein equation, g mu nu equals lambda g mu nu. And we can write it as, we can write it by starting with 5-dimensional Minkowski space, ds5 squared, whose line element is dx0 squared plus dx1 squared, dx2 squared. So just the flat line element, 5-dimensional Minkowski space. And then impose the constraint that x0 minus x0 squared plus x1 squared plus x2 squared plus x3 squared plus x4 squared equals L squared, where L is the de Sitter radius. So this is a hyperboloid in 5-dimensional Minkowski space. And of course, so it has a symmetry of SO4, 1. And now we don't need, it's a maximally symmetric space. We don't need 5 coordinates, x0, x to x4, to describe a 4-dimensional space-time. So we can write, we can simplify by, well, the metric gets a lot more complicated looking, but we can eliminate one of the variables by writing x0 as sinh tau, x1 is cosine theta, theta being an angle, and tau is going to be time. Theta is going to be the angle on a 3-sphere. Cosh tau, x2 is sine theta, cosine phi. We're going to need 2 angles. Cosine phi, cosh tau. Sorry, 3 angles. And then x3 is sine theta, sine phi, cosine psi, cosh tau. And finally, x4 is equal to sine theta, sine phi, cosine psi, cosh tau. Okay, so it's easy to check that for any of the 4 values, I need an L in front of all these. So it's easy to check that for any value of theta, phi, psi, and tau, that these x0 through x4 obey this equation. Yes? Yeah, sorry, sine psi. Thank you. And so that they obey this equation. And when you plug this into that top line element, you get that ds4 squared is equal to minus d tau squared plus cosh squared tau d omega 3 squared. So it looks like this. Tau equals constant, obviously, is a 3-sphere. And so these are global coordinates on de Sitter space. Tau equals constant. This would be tau equals 0. And we can see that the spheres get bigger and bigger as we as tau goes to plus or minus infinity. So it's expanding in the far past, expanding in the far future. Now, but we want to understand the causal structure. And so to do that, we write that, let's write cosh tau is equal to 1 over cosine of t. So that when minus infinity is infinity less than tau goes to infinity, we have t goes from minus pi over 2 is less than t is less than pi over 2. And now if we do the coordinate transformation, we find that ds4 squared is equal to 1 over cosine squared t minus dt squared plus d omega 3 squared. Okay, so now we can get rid of this factor by conformal transformation without affecting the causal structure. And this is now ds tilde 4 squared. And so now we can investigate the causal structure by letting t run over this range and looking at the causal structure of ds tilde squared. So how do we write ds tilde squared? Well, that turns out that it's just a square where t is running from minus pi over 2 to 2 to pi over 2. And theta, OK, we could also take theta to run from minus pi over 2 to 2. So let's also take theta to run from minus pi over 2 to plus pi over 2. And then we've suppressed the two-sphere parametrized by psi and phi. Now, if we look at this, when theta is equal to 0, no, I think I wanted theta to go from 0 to pi. When theta is equal to 0, we can see that there's a sine theta. There's a sine theta in front of the two-sphere there. And so, right, if we wrote out this line element here, it would have a sine squared theta in it. So the two spheres are going to 0 at the boundaries, and they're getting smaller at the end. So we have a sequence of two spheres which are closed up at either end. So this line is an S3. OK, now if we're not changing, if we're just staying at a fixed point on the two-sphere, if we're not changing phi and psi, then we can have a null geodesic will go at 45 degrees, like this, for example. So one thing we learned from this picture, so again, not very obvious, a lot of things we learned from this picture, that if you have this three-sphere, every slice of de Sitter space is a three-sphere. And if you start at the, let's say the north pole is theta equals 0, and the south pole is theta equals pi, over the entire lifetime of the universe, you can get only from the north pole to the south pole. You can't get back, a light ray can't get back to the, I mean, if it turns around, it can get back, but a null geodesic can't go from the north pole to the south pole. Moreover, when you get any point at future infinity. So this is now both I plus, and it's also equal to scry plus. Okay, so any light ray, if a light ray goes here, this isn't a special point on the 3 sphere. It's just going to reflect off, just like over here. We don't stop the light. We stop the light rays when they get to here because that's infinity, and that's the end of the space-time. And you can show that this is what's called geodesically complete. That is, that the affine parameters on the geodesics will run to infinity by the time you get out there. So you don't want to extend this space anymore. But when you get to here, it's just a finite affine parameter, so you need a boundary condition, and your light rays will go back out. So it's the same thing here in this diagram, where the light ray that comes over to here will go up like this. And so you can see that only part of, you don't have all of the causal past if you're anywhere at scry plus, which is the same thing as I plus, and there is no spatial infinity. Anywhere in the past is less than the entire universe. So there are always going to be regions that you can never, that are never in your past, no longer how you wait. That's just saying that there's points in the universe whose distance from us, whose closest distance from us is increasing faster than the speed of light. So we'll never be able to see them. Okay, so that's basically the Penrose diagram of de Sitter space. But it's also useful to look at a different coordinate system for de Sitter space. And that's if we take what's often called planar coordinates, or the flat slicing of de Sitter space. So here we have x0 over L is equal to sinh tau plus a half x squared. That's, where these are 3 different x's, new x's, e to the t, and x1, the original x1, x2, x3 is x e to the t, and x4 is cosh t minus a half x squared e to the t. Now if we plug back into the formula that's underneath there, that one there, we get that ds squared is equal to minus dt squared plus e to the 2t dx squared. Okay, so now this coordinate system, what's the relationship between this and this? Well, one can show that this coordinate system only covers, let me draw this Penrose diagram here, the same Penrose diagram, lines of constant t look like this.
So, sorry, this is a t, not a tau. All right, so lines of constant t look like this. And this coordinate system only covers, so this is a commonly used coordinate system for studying de Sitter space. And this coordinate system only covers half of the full Penrose diagram, and it's the expanding half, or an expanding half. You see, in this coordinate system, you only see that de Sitter space is expanding. And this is a coordinate system frequently used, more often used by cosmologists than this one that I wrote down up there. And there's something else to say about this. Suppose you had some dust in here. So I want to go from this to what the Penrose diagram would be for an expanding cosmology, something like our own. That's my goal here. So suppose you had some dust in the universe. Well, as you go backwards in time, the universe is exponentially contracted. And by going backwards in time, I mean here along these constant time slices. And it gets more and more dense. And in fact, it gets infinitely dense here. And so we can't use the Einstein equation. And so there's a singularity. That's how one usually models the Big Bang singularity. And somewhere down here, there might also be an inflationary region squeezed into there. But this would be, up here, we just have the Einstein equation, and we would have the late time de Sitter behavior. And here, we have the Big Bang. And it's only the very last slice at t equals minus infinity that becomes null in this de Sitter diagram. And the Einstein equations break down because the matter would get too dense before you got to there. So this Big Bang singularity is really one of these space-like. All these lines are really space-like. So I have a space-like Big Bang singularity. So this is the Penrose diagram. This is sort of the astronomer's best guess for the Penrose diagram, the causal structure of our own universe. Late time, it looks like de Sitter space. There's some early time thing where quantum gravity becomes important, or inflationary, or there's new degrees of freedom. We just lump that, call it a singularity, where we don't allow, we don't know the laws of physics. There could be white elephants attached down here for all we know. Anything could happen beyond that. But we just draw a line where we can't use the laws of physics and call it a singularity. That's, of course, what a singularity is, a place where the laws of physics break down.
Why do you people say it was a space-like? I guess assuming that the singularity really is happening when you approach that null boundary.
No, it happens before you approach the null boundary. So it's a feature of our universe that an observational feature of our universe that the density is roughly constant along slices of some constant t, this t, right? There isn't, right. You can't have you can have a de Sitter invariant distribution of dark energy, of course, because dark energy is just lambda, but you can't have a de Sitter invariant distribution of dust.
But what about
It always picks out a time.
inflationary period then being right before, right?
Well, so if you put an inflation period here, so if you have if you have some inflationary model, if you perturb it even a little bit, with the presence of some matter is you go back. This is a theorem of Guth and Vilenkin, I think. As you go back, you ultimately, I mean, of course, Hawking proved theorems like that before you, without the dark energy, but they did it. So you go back, you still ultimately get a singularity. So the only way, if you include inflation, the only way that this diagram ends is that it doesn't change the causal structure, actually. The only way that this diagram ends is that there's a little band. We could label these, you know, exit of inflation. So we exit inflation along some band like that, and then we go back to, yeah, and then, yeah. Okay, so finally we get to anti-de Sitter space, which and for simplicity, so I'm just going to write down the two-dimensional example. And the two-dimensional example, so we have lambda is, we can construct it as hyperboloids like this, but with a different signature. But let me just write down the metric. If we have lambda is -3 over L squared, and we look for constant negative curvature metrics in 2 dimensions, I could do it in 4 dimensions, but I think by now you see how these spheres go along and sort of go along for the ride. We'll have spheres which go along for the ride. And so we'll have ds squared is equal to L squared over y squared. Minus dt squared plus dy squared. These coordinates don't cover all of anti-de Sitter space. I'll give some that do in a second. And now we want to go to null coordinates. U equals t minus y, v equals t plus y. And we get that ds squared is equal to minus du dv. Let me just drop the L's. Minus du dv over 4u minus v squared. And now we do what we did before, where we take u is equal to tangent of u tilde and v is equal to tangent of v tilde. And now I'm going to write, then I get ds squared is equal to 1 over sine squared u tilde minus v tilde minus du tilde dv tilde. Okay, and I can now also write this in terms of tau and sigma, where I take u equals a half tau minus sigma, v equals a half tau plus sigma, and then I have that ds squared is equal to 1 over sine squared sigma minus d tau squared plus d sigma squared. Okay, so first thing to say is this metric is obviously okay. except it's sigma equals 0 or pi. Okay, so we have to worry about sigma equals 0 or pi. We'll come back to that in a moment. But obviously, I can let tau go from plus or minus infinity. So let me, without any problems. And so this, what happens at sigma equals 0 or pi? Well, if we look at the distance, so here's tau, and we have sigma going this way from 0 to pi, and it's clear that that tau equals plus or minus sigma are the null geodesics, so they're going at 45 degrees. But what happens at sigma equals 0 or pi? Well, the first thing is that if we compute the distance from any finite point, sigma naught, let's look at the distance to this boundary, but let's not go all the way to 0, epsilon. We have to take the square root of g, so we take the proper distance is d sigma over sine sigma. And so that'll go like near sigma equals 0. That'll have a divergence that goes like log epsilon. Okay, so the distance to sigma equals 0 and sigma equals pi is infinite along a space-like trajectory. Okay, but now there's something a little funny. So these lines are like infinity. But let me just draw again here. If we had two-dimensional Minkowski space, well, we had more, ignore the extra spheres, we'd have this same. The only difference we'd have if we put the spheres in would be that their volume would be going to infinity as we got to, they would also have powers of sine sigma, and the sphere's volume would be going to infinity at these two boundaries. Okay, so if you go with spatial infinity, you just have this one point in Minkowski space. But in anti-de Sitter space, there's all kinds of different points you can go to at spatial infinity. And moreover, let's suppose we send a light ray. Well, we know light rays go at 45 degrees. So let's send a light ray to the boundary. Let's sit at the middle at pi over 2. Send a light ray to the boundary, and then arrange for a friend to be out there with a mirror and to reflect it back. And then we get to see that light ray at some, well, if this is tau 0, this will be tau 0 plus pi. Okay, so we can get a message from our friend who's infinitely far away in a finite amount of time. Weird property of anti-de Sitter space. Now, this also means that so anti-de Sitter space is very different in this sense. This also means, suppose we want to solve, suppose let me go back to Minkowski space. Suppose we want to solve the wave equation in Minkowski space, and say the scalar wave equation or the Maxwell equation. So then we impose initial data at t equals 0, and a slice of some later time, looks like this, right? A space-like slice always goes out to spatial infinity, I0. And basically, if you have a space-like slice, the initial data for the wave equation will determine everything in what's called the domain of causal dependence of the slice. So if here's, suppose I take Minkowski space again, and I just draw a little piece here, and I tell you what phi, scalar field phi, and phi dot are, and I just want to solve the massless wave equation everywhere on this slice. That's the initial data that you need to impose. Second order differential equation, you need two pieces of initial data. Well, disturbances can't propagate faster than the speed of light. So if you take the light cone of the endpoints, basically that initial data will determine the solution everywhere inside this domain of dependence. You can't hope to determine it out here because we could have some disturbance in the field which could get there. But there's no disturbance which can get to this region without passing through and affecting the data on the slice. So the data on the slice determines everything in the domain of dependence. And when you make it a slice that goes all the way to complete space-like slice that goes all the way to spatial infinity, then that means that if you give all the data on such a space-like slice, you determine the complete wave function of the scalar field everywhere to the future of that slice. Not true here. So if we take a complete space-like slice in anti-de Sitter space, so it's infinitely big, it goes on forever, it's an infinite distance to these boundaries. Take a complete space-like slice, we still only determine the data up to here because stuff can come in from the boundaries. So one often says that anti-de Sitter space is not a globally hyperbolic space-time because the initial data doesn't determine the future evolution. And that used to be, anti-de Sitter space has been studied for a long time, and people used to think it was a little bit weird and slightly uninteresting because, it's not globally hyperbolic and weird stuff. You have to impose extra. What do you have to do to fix this? Well, the way you can fix this is you can impose some boundary conditions here. So you can, put Neumann or Dirichlet boundary. If it's a massless scalar field, you can put Neumann or Dirichlet boundary conditions there, which basically, in some, they say that nothing can come in from the boundary, and they also tell you how things reflect off the boundary, what the phases are of things that reflect off the boundary. So the study of how you apply boundary conditions in anti-de Sitter space has been a huge subject for the last 20 years, and there are different choices that lead to different physical physical theories. But so this is another thing that can happen when you're studying the causal structure of a space-time. You might find that there are regions that can't be determined from the initial data. And indeed, the focus of this course is black holes. One will find that there are regions in the interior of the black hole that are not, it's a little more complicated than this, but they're not determined from, they can't be determined by initial data on some global Cauchy slice before the black hole has been formed. Okay, so I think that's about all I'm going to say about anti-de Sitter space. And I'm about to move on to black holes, but maybe this is a good time to pause for questions and take a sip of my coffee if it's not all gone. No, it's not. Any questions? Okay. So, well, we don't have too much time, but might as well start. So, finally, we get to black holes. And all right, so there are black holes in all dimensions, in general relativity, in all dimensions. We live in 4 dimensions. I'm going to start with that. But later on in the course, it turns out that black holes in lower dimensions are really interesting. That's something that's only been understood in the last 20, 30 years. And there's a lot, they're in many ways much simpler. And there's a lot that you can learn. A lot of things that are too complicated to put into concrete equations in 4 dimensions and can be made very concrete in lower numbers of dimensions. And so a lot of the course will be doing that at 3 and 2 dimensions, very different things that you can learn in 3 dimensions and in 2 dimensions, sort of weird and surprising how different it is. In higher dimensions, they seem to sort of get less interesting. I don't think as much has been learned by looking at higher dimensional black holes, but there's certainly one of the things that has been learned is some things like cosmic censorship and so on are simply not true in higher dimensions. Yeah, we'll mostly be 4 and below. Certainly for the next couple lectures, it'll all be 4. And what are the classic black hole solutions? Well, first of all, there's the Schwarzschild solution. So that is characterized simply by a mass m. It's spherically symmetric, and it has no charge or angular momentum. That's the simplest solution. The next simplest solution is the so-called Riesner-Nordström solution. Which has m and q non-zero, but no spin. And then there's the Kerr solution, which has j not equal to 0, m and j not equal to 0, but q equals 0. And then finally there's Kerr-Newman, the general solution, which has charge, mass, and angular momentum, all not equal to 0. Now, for astrophysical purposes, the most interesting one are the Kerr solutions, because there's no reason why it would be very weird. There's no reason why a black hole should ever have no angular momentum at all. It would be spinning at least a little bit. Why would it be exactly not spinning? Okay, maybe somebody will find one that is exactly not spinning, but typically they form in complicated processes and they're made with angular momentum. And indeed, it's known that their interactions with other random astrophysical objects have a tendency to spin them up, preferentially spin them up rather than spin them down. So real astrophysical black holes are Kerr black holes. Nevertheless, we'll start with Schwarzschild, which is way, 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 way simpler than Kerr. So, Schwarzschild, as I said, was found in, a few months after Einstein wrote down his field equation at the beginning of the 20th century. The Kerr solution is kind of a miracle. It's like the most Yao said to me, it could be the most non-trivial known exact solution of a nonlinear differential equation ever. And so, nobody who teaches general relativity ever derives that it's a solution because it takes too long. But nevertheless, you can write it down in closed form and in terms of these trigonometric functions, and there it is. So it took 50 years, not months. It took 50 years and many people to find, and actually there was no reason that there had to be a closed form solution. We don't know now why it had to be true. It could have been that, like the mass of the proton. There's never going to be a closed formula for the mass of the proton. You just have to put the thing on the computer and simulate it. Okay, maybe somebody will find one. I don't think so. Okay, so, but there was no reason there had to be a Kerr solution, and but Kerr found it, and there it is, and it's been sort of astonishing people ever since, and it has all sorts of, then he finds the solution, then it turns out the wave equation separates in the solution for still mysterious reasons, and so there's all kinds of beautiful magical stuff that happens with this Kerr solution, and I don't think it's just fun and games. I think that these properties, all these wonderful properties of Kerr and what their ultimate origin is, are going to be a piece of sort of a deeper understanding of what a black hole is. But it is way more complicated than Riester-Nordström, which I think, because Riester-Nordström still. Do you have questions, Sabrina?
Do they have magnetically charged monopole versions of these?
Well, we're just talking about electromagnetism.
But just magnetic monopole version, because then you can't use the neutralization argument that you might, so it's massive then it's magnetic.
Okay, so the solution would be the same.
Yeah.
The metric would be the same because you would just dualize the field strength from electric to magnetic. Now, would you?
That assumes that all the charges that are light are
Well, I think if there are magnetically charged we don't really know. Nobody's ever seen a magnetic monopole.
But then it would
But
neutralize, which would be a good thing, I guess.
well, if there are magnetically charged black holes around, there's probably also some heavy magnetically charged particle, which we just haven't seen yet. And then that would, that would also neutralize it. But who knows? So this is also not too much more complicated than this one, actually, and so we'll study that second, and then we'll talk about the Kerr solution and then the Kerr-Newman solution, and I guess what we'll do. It's coming to 6 o'clock now, but I guess what we're going to do next time is, we want to talk about, we'll derive the Penrose diagram for Schwarzschild. And then also we want to talk about, there's something funny about these Penrose diagrams. We're also going to want to talk about gravitational collapse. So I guess my timing was good. Is that a fire alarm? A snow alarm?